All right, here we go. So this is the first of 3 little videos that I'm going to do with examples of Lewis structures. Okay, so we just did a video where we went ahead and kind of explained through octet rule, electron dot stuff to kind of led us up to the Lewis structures. Lewis structure is the big thing. We talked about these 6 steps here, and I just did one example for you. So I'm going to do a few more examples with you to let you kind of get the hang of it. Some of these examples may be problems that you find on the worksheet, or they're very similar to a problem that you'll find on the worksheets that I have for you. Okay? So the first one we're going to look at here is ammonia, which is NH3. Okay? So step 1 is determining the type and the number of atoms that we have. So we have 1 nitrogen and we have 3 hydrogens, right? Step 2 is to figure out how many valence electrons do we have to work with, okay? So if you look on your periodic table, you will find nitrogen to be in group 15, okay? So real quick, I can show you. It's in group 15 right here. So remember, 1 valence electron, 2 valence electrons. We kind of ignore the D group. It's kind of weird a little bit. You don't have to worry about that. And then start back up here, the rest of these main group elements. 13 has 3, group 14 has 4, group 15 has 5, 16 has 6, 17 has 7. And in fact, a lot of times these are called group 1A, 2A, and then up under here it says 3A. It's group 13, but it's 3A. Okay, there's like A group elements, and then down here it's group B elements. But anyhow, so for these, if you just take the group number here and subtract it by 10, that tells you the number of valence electrons, if you haven't figured that out yet. Anyhow, nitrogen has 5. So we have 5 for the nitrogen, and then once again, hydrogen has 1 electron, right? So 1, and once again, there's 3 hydrogens, so each one of those has 1. So 3 of them, they each have 1. That gives me 3 electrons, plus the 5 more from nitrogen, gives me a total of 8. So if I come back to the steps here, that's what we're working with. We're working with 8 total valence electrons. All right. So the next thing we would do is we would make our skeletal structure. I only have nitrogen and hydrogen. Hydrogen can never be a central atom, so that makes it easy for me to say, okay, nitrogen's in the middle, and then around nitrogen, I'm just going to put the hydrogens. And it doesn't matter. You know, you've got 3 of them, you've got 4 sides. It doesn't matter what 3 sides you put it on, okay? And it's just there it is, all right? The next thing we have to do, because that's done, we've got our skeletal structure built using the least electronegative element in the middle, and then putting everything else around, all right? The next thing we have to do is we have to take and we have to fill it up and give everybody 8 that won't take, okay? Remember, hydrogen is a set it and forget it guy. We don't have to worry about giving them any more. All he can hold is 2. He's sharing the 2 right here with the nitrogen. This guy's sharing the 2 with the nitrogen. This guy's sharing the 2 with the nitrogen. But all the other elements, we have to make sure they have 8. Okay? So the only other element here is the nitrogen, right? So nitrogen right now has 2, 4, 6. So we need to give him 2 more to get him to be completely filled, to fill that octet for him. Now he has his 8. All right? So we've done step 4. Step 4 is complete. Step 5 is for us to simply count how many electrons that we used in this process. So 2, 4, 6, 8. Remember that a bond is a pair of electrons. A single bond is a pair of electrons. There's technically an electron on each end here, if you want to think about it like that. Okay? So a line is a pair of electrons. So we got 2, 4, 6, 8. And then we compare that to step 2. How many were we supposed to use? We were supposed to use 8. So we're good. We used the correct number of electrons. So everybody's happy, and the nitrogen or the hydrogens are each happy because they got the 2 they want. This nitrogen's happy because he has the 8 that he wants. That's what we took care of in step 4, right? And the whole system is happy because we used the correct number of electrons, okay? So if you have each of the atoms being happy, given the correct number of electrons that they wanted, and you have the whole system being happy, having the total number of electrons that they want, there's a real good chance that we got it right, okay? There's some other things there that could go wrong, but there's a real good chance if we get the total number right and we get each one of them having the number they want, then we're good to go, all right? Once again, formal charge wouldn't change anything here. I'm going to wait a couple videos to talk to you about that, but I'll let you know when you need to worry about that, all right? So now this would be the Lewis structure for ammonia, or in other words, NH3. All right, let's look at the next example. The next example would be phosphorus trifluoride, or PF3. So PF3. Go through those same steps again. Okay, you'll get a little bit quicker going through here. I'll try not to speed myself up too fast through here. All right, so the first thing, we've got one of these, we have three of these. All right. So how many valence electrons is this guy? Look on your periodic table. As you're watching this video, it's probably good to open up your textbook or pull out the periodic table that I've given you so you can look on there and you can see real quick, hey, this is where it is. That's why he's saying the number of valence electrons, okay? So phosphorus, once again, it's right up under nitrogen. It also has 5, okay? And then fluorine is in group 17. Fluorine actually has 7. So there's 7. And there's 3 of them. There's 3 fluorines. So each of the fluorines has 7 valence electrons. 7 times 3, that's 21. Plus 5 more gives me 26, right? 21 plus 5, 26. So I'm using a total of 26 electrons here for this guy, all right? So we know how many electrons, we know what we're working with. Now we have to build our skeletal structure. So we got to decide. Okay, we've got 4 atoms here. We've got a phosphorus and we have 3 fluorines. Which one of them goes in the middle? Does one of the fluorines go in the middle, or does the phosphorus go in the middle? There's not a central atom of carbon, so we don't have to worry about that. But we're looking for the least electronegative atom. Oops. So if you go to your periodic table, page 161, or the one I give you, you can look and you say, okay, fluorine is a 4.0. All right, it's got the highest electronegativity. And phosphorus is actually only at 2.1. I know you probably can't read this as I'm pointing at it, but you can look at your copy. 2.1. So this guy would have a lower electronegativity. That would be the one in the center. Okay, I mentioned it before. I'll say it again. Phosphorus also wants more bonds, okay? So it makes sense for it to be in the middle. Fluorine, having 7 valence electrons, really only wants 1 more bond. So it wouldn't make sense to put fluorine in the middle and have it bonded in several things, because fluorine just wants to pick up 1 more electron, and that means just having 1 more bond, okay? So phosphorus is in the middle, and then around, we're going to put the fluorines. Once again, we'll put it up there. Don't quite have room. Doesn't matter what 3 sides you put it on, but there it is. All right. So we've got step 3 done. We've arranged this kind of skeletal structure. We have 1 of these guys. We have 3 of these guys, just like we're supposed to. Step 4 goes on and says, okay, everybody that don't have A, give them A. Right. So if we come around here, this fluorine just has these 2. So 4, 6. 8, that's good. This fluorine just has the 2, so that makes 4, that makes 6, that makes 8. This fluorine, theirs, and that makes 8 for that. So all of these guys have 8. Now we look at the phosphorus in the middle. It only has 2, 4, 6, and yes, I'm counting these 2 with this guy and with this guy because they're sharing, remember, right? It's the magic of covalent bonds. It allows you to use fewer electrons, but feel like you have more electrons. All right. My wife has 4 kids. I also have 4 kids. That doesn't mean we have 8 kids. We have 4 kids in total, but we each have 4 kids. Does that make sense? Okay. Need to give this guy 2. So 2, 4, 6, 8. Now, everybody has 8, right? So this guy's got 8, this guy's got 8, this guy's got 8, and this guy here has 8. So We've got step 4 done. We give everybody 8. We filled everybody's octet. So as far as the individual atoms being happy, we've accomplished that. Now we need to check step 5 and say, okay, is the system happy? Did I use the correct number of electrons? Because I can't just make up electrons. That doesn't work that way, right? Or just get rid of electrons. So how many total electrons? So I got 8, and 8 is 16, and then 8 more is 24, right? If you need to count them individually, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then don't forget we haven't counted this guy yet, 26, okay? 8 is 24, plus these two give me 26. So I did use the correct number. I was supposed to use 26. I did use 26. Excellent. These easy problems, these kind of first example type problems, they're just kind of going to work out. When you build them, single bonds, everything just works. Put single bonds, give everybody 8 that needs to have 8, and it's right. We're good. So there's that. Ta-da! This would be the Lewis structure for this phosphorus trifluoride. Okay? A couple more examples we're going to do just to make sure that we're good. If you need to back it up, back the video up, if you need to pause it, do whatever you got to do to make sure that I'm not getting ahead of you here. So next problem we're going to do is water, H2O. Okay, so we've got 2 hydrogens, we have 1 oxygen. In terms of hydrogen, this bad boy only has 1 valence electron, but there is 2 of them, right? And then oxygen, you'll find oxygen group 16, so oxygen has 6 valence electrons. So 6 plus these 2 gives me a total of 8. So I got 8 electrons I'm working with. In terms of the step 3, I can't have hydrogen in the middle. Oxygen has to be the one in the middle. If you look in terms of electronegativity, hydrogen actually has a lower electronegativity than oxygen, but it doesn't matter. Hydrogen can never be the central atom, okay? Because it can only have 1 bond. So you have your oxygen in the middle, and you've got your hydrogens bonded to it. Once again, it doesn't matter where you put them, they're bonded. All right? So there's that. All right, so we've got our structure built, oxygen in the middle, because hydrogens can't be, all right, and your 2 hydrogens on each side. We have 1 of these, we have 2 of these, I'm good to go. The skeletal structure is built. Next thing to do is give everybody 8 that needs to have 8. These guys don't. Common mistake is people just start putting dots, and they put these dots around the hydrogen, and you end up with 8 electrons around hydrogen, but that doesn't make any sense. Hydrogen just wants 1 more electron to have that first energy level completely filled, because that first energy level, that first s orbital only holds 2 electrons, right? So it's good, and this guy's good. It's just this guy that has 2, 4, so we need to go 6, 8 to make that oxygen happy. Now when we do that, we've completed step 4. These guys, set them, forget them, we're good. And now this oxygen's got 2, 4, 6, 8 electrons. In terms of each of the individual atoms, we're good. Just need to check step 5, is check the system, count the total number of electrons I've used, compare that to see if it's equal to the number of electrons I was supposed to use. Of course, 2, 4, 6, 8 is how many I used, it's how many I was supposed to use. So step 5, we're good. We didn't have to do any adjusting. None of these problems so far we've had to do any adjustments by adding bonds or taking away bonds, okay? And then once again, formal charge, we'll get to that a little bit later. So, hey, we're good. This would be water, okay? If we talk about molecular geometry, which we talked about in a video before, this atom would actually be bent, and you've probably seen some water molecules where it wasn't straight out like this, it was actually bent around like that. But we're not getting into that. In more advanced chemistry classes, they'll have you draw them kind of with the correct molecular structure, molecular geometry, but we're not doing molecular geometry, so we're just straight across here, we're good. Even if you took this hydrogen and put it down here and put these other oxygens over here, that's fine. Okay, everything for us is pretty much just going to be these 4 sides, like 90-degree angles, things and stuff. Okay? All right. I'll do one more with you because I feel like you got this going on. So we're going to go CH3OH. All right. So this one looks a little bit funny. Okay. The thing that looks funny about it is that you have 3 H's here, and you have another H over here. So why didn't we say CH4O? Right? If you ever see anything like this, and this would be, this is a hydrocarbon where you have some hydrogens and carbons bonded. Sometimes there's oxygens in there too. Anytime you see this OH separately, it is giving you a hint to the structure, the way it's built, that this hydrogen is probably going to be bonded to this oxygen and not bonded to the same thing that these hydrogens are. Okay, so it's kind of giving you a hint by separating it out. Technically, it's like you got a hydroxide over here that's bonded with this stuff, but anyhow, I might be getting a little bit past you. All right, so step one, we have one of these. We have a total of 4 hydrogens, and then we have 1 oxygen. Right. So in terms of valence electrons, carbon is a 4, right? It's group 14. And then hydrogen is a 1, and there's 3 plus this one more. There's 4 of them. And then the oxygen is a group 16, so there's 6 valence electrons there, right? And if we add that up, 4 and 4 gives me 8, and 8 and 6 gives me, 14. Okay? Now, the next thing to do would be to build my structure. Remember, if carbon is there, it's the central atom. So I've got carbon. All right? But what you will notice is that I've got 3, 4, 5 atoms beyond carbon. Well, carbon only has 4 sides, right? So without getting any weird exception kind of problems, that means I can only bond 4 things to carbon, right? Make sense? Well, I have 5 things, so I can only bond 4 of them to carbon. If I start doing this, I go hydrogen, 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 just putting single bonds on everything, hydrogen. If I do like that, then I kind of back myself into a corner. I'm stuck. I don't have anywhere to put the oxygens because each of these hydrogens can only have 1 bond. So I can't come off beside this hydrogen and bond more stuff. And hydrogen is like a dead-end road. It's the end of the line. I can't go on beyond that. All right? So though I can do that with 3 of them, this oxygen needs to be bonded to the carbon. Okay? The difference between the hydrogens and the oxygen is the oxygens don't have to be a dead-end road. You can go on beyond oxygen. Oxygen can have more than 1 bond. It actually wants more than 1 bond. Okay? So 3 hydrogens bonded to the carbon, and then 1 of the oxygens, or the oxygen, bonded to the carbon as well. And then I can come on the other side of the oxygen, and I can dead end that road into the hydrogen. Okay? And once again, this hydrogen being separated from these 3 hinted to me that this was going to be the case. That a hydrogen was going to be bonded to the oxygen, and then the other would be bonded to your central atom. Okay? Carbon's still my central atom. I just couldn't fit everything around carbon because I could only fit 4 things there. Alright? So the skeletal structure part might be a little bit more tricky on this problem, but if you play with it a little bit, I think you figure out there's only one way it works. Okay? Now, as far as this hydrogen being here or here, that doesn't really matter. This OH could be down here or over here. That doesn't matter either. Okay? But 3 hydrogens stuck to the carbon, an oxygen bonded to the carbon, and then the other hydrogen bonded to the oxygen. All right? That's my skeletal structure. Now, step 4, give everybody 8 that don't have 8. All right? So this guy, carbon's got 2, 4, 6, 8. It's happy. Hydrogens, they're automatically happy. This oxygen here has got 2, 4. So I need to go 6, 8. Everything's in pairs here with these electrons. Okay? 6, 8. Just like so. Okay? 2, 4, 6, 8, 10, 12, 14. Step 5 says, count how many you have. I just counted 14. 2, 4, 6, 8, 10, 12, 14. How many was I supposed to use? 14. So the system's happy. Each of these guys are happy. They all have the number they want. And I used the correct number in total. So the whole system's happy. Right? So this would be my formula for this CH3OH. Okay? This would be my structure. Excuse me, my little structure. All right? We'll do another video with problems that have some double bonds and triple bonds and stuff. All of these so far have just been single bonds. And then we'll do another one where we have to adjust considering the formal charge and that kind of thing. Okay?